Hello everyone, let's talk about the electromagnetic spectrum, a slightly shorter video for you today. You're already aware of the electromagnetic spectrum. Hopefully you can put the parts of the spectrum in the correct order, and you're aware of some of the uses and applications of each part of the electromagnetic spectrum. What we want to consider today is just really the nature of an electromagnetic wave. And the first thing to say is that it is not a mechanical wave. So two examples of mechanical waves would be sound. Sound is longitudinal, so it requires a medium. The medium is air, and those air particles are vibrating parallel to the direction of energy transfer. Water would be a mechanical wave. It's transverse. The water particles are oscillating at 90 degrees to the direction of energy transfer. But electromagnetic waves are not mechanical. There is nothing physically, there's no substance or medium physically oscillating. It is the variation of two different fields, an electric field and a magnetic field. And one of the things that we'll look at next year when we study both of these types of field in much more detail is the fact that energy can be stored in fields. And so energy is transferred with an electromagnetic wave because the energy is stored in those electric and magnetic fields. So what does an electromagnetic wave look like then if it is not the variation or the oscillation of actual substance? It's the variation or oscillation of magnetic and electric fields. And so if you have a look at this diagram, you'll notice that the two fields are at right angles to each other. There's a 90-degree angle between the way the electric field and the magnetic field are oscillating. The electric field looks like it's kind of oscillating vertically, and the magnetic field looks like it's oscillating horizontally, and it looks like they're in phase. It looks like the peak of one wave matches the peak of the other wave. In other words, there is zero phase difference between the two of them. And that is the nature of an electromagnetic wave. It is the propagation of electric and magnetic fields, which are varying sinusoidally, and the electric and magnetic fields are oscillating at right angles to each other. And of course, the other property that you looked at with respect to electromagnetic waves is that they can travel through a vacuum because they don't need an actual substance to oscillate. They can travel through a vacuum, and obviously the evidence you've got from that is that X-rays and ultraviolet and infrared and visible light all travel through space, and so they need no vacuum. There's a common property, isn't there, for all electromagnetic waves, which is that they travel at the speed of light, 3 times 10 to the 8 meters per second. Now, you need to be aware of the wavelengths of each part of the spectrum. So there is the spectrum, and if you were to be provided with a wavelength of a wave, you would need to be able to identify exactly which part of the spectrum it's relating to. So that's a piece of work that you're going to be looking at following this video. One final thing to kind of say about the electromagnetic spectrum is it's not kind of like discrete sections, it's a continuum. In other words, visible light is no different to gamma or X-rays in the sense that, but all of them are variations of electric and magnetic fields. I guess the reason that visible light is different to an X-ray is it's all about how it interacts with matter. And so we kind of divide the spectrum up into regions based on how it kind of interacts with matter. Okay, so you know that an X-ray is ionizing. You know that the density of a substance determines whether or not an X-ray will travel through it. You know, conversely, that radio waves are not ionizing, and the way that radio waves interact with matter is really different. So it's a continuum, and it's based on wavelength, or frequency, I guess. And one of the things that you're going to do following this is to do a little quick bit of research, and you're going to come up with the range of wavelengths for each part of the spectrum. And you are going to need to learn those, so that if I tell you I've got a wave and it's traveling and it's got a wavelength of 3 centimeters, you need to be at the point where you kind of go, I know what that is. That's a microwave. Okay, thanks for your time.